Hi everyone, my name is Zeynep Yoldaş and I am a freshman at Bilkent University in the Department of Electrical and Electronics Engineering. In this video, I will present my Physics 101 lab project, which is about the independence of pendulum period from mass.
According to the formula, the period of a pendulum is unaffected by changes in the mass, as long as the length of the string and the gravitational acceleration remain constant. In this experiment, we aim to confirm this theoretical relationship by using different masses and observing their effect on the pendulum's period. Also, in this experiment, the motion of the pendulum was treated as simple harmonic motion. To keep this approximation valid, the pendulum's angular displacement was limited to 15 degrees. This is important because at small angles, the restoring force is nearly proportional to the displacement, but at large angles, this proportionality no longer holds, leading to potential errors, which we avoid by restricting our angle to 15 degrees. For this experiment, we will be using a pendulum stand, a string of length 30 centimeters, a protractor to measure the release angle, a device capable of recording video, a device for slow motion playback, an analytical balance to measure the masses accurately, and a set of masses.
Also, we used slow motion video playback at half the normal speed. This helped us to capture short time intervals more accurately. We recorded the time for 2 oscillations and then calculated the average period for one. And then we also divided the founded data by 2 to return back to the original speed.
As can be seen in this video, I have released the mass from a fixed angle, which is approximately about 10 degrees, and I have repeated the same process for different masses. The data collected was organized into tables and plotted on a graph of mass versus period. According to theory, the graph should produce a horizontal line, showing that the period is independent of mass. The theoretical period was calculated to be 1.1 seconds, while the average experimental value across 6 masses was 1.0207 seconds. This small difference confirms the reliability of the results, as the observed error percentages were minimal, and the periods varied only slightly. They remained in a range of 1.02 to 1.13 seconds.
Despite efforts to minimize inaccuracies, some errors were unavoidable, such as, in some trials, the masses rotated upon release, introducing unintended forces such as centripetal force or the torque effect. This was tried to mitigate it by resampling the process to achieve cleaner oscillations, or in some others, slight variations in how the pendulum was released, for example, whether there was an accidental initial force exist or not, could have affected the motion. And throughout the experiment, air resistance and friction at the pivot point were not taken into account, but they could still have slightly altered the results. In conclusion, the experiment confirmed the theoretical prediction that the period of a pendulum is independent of its mass. The graph and data strongly support this relationship, with the theoretical period closely matching the experimental results. While some errors were observed, the use of slow motion playback, multiple trials, and careful measurements minimized their impact. The results not only validate the theoretical model, but also underscore the importance of precision and thoughtful experimental design in physics. Further refinements, such as using automated timing systems or mechanical release mechanisms, could further improve accuracy. Thank you for watching my presentation.